Hi, everyone. It's great to be here today. So, what I'd like to talk about today is how we have drawn on ideas and perspectives from NDM in our research on accident and incident analysis. Now, I work for the Australian Department of Defence, largely on Air Force projects. And so I'll talk about these ideas in a military aviation context, but I think these ideas may be applied usefully in many other systems as well. And so I'll begin by talking about some ideas from NDM and then how we've applied them and what we've discovered. So a key NDM perspective we've adopted in our research is captured nicely, I think, in a paper written by Gary Klein and Corinne Wright. And they wrote that good performance is much more than the absence of mistakes. Now, they were reflecting specifically on the contrasting perspective of expertise in the heuristics and biases community. And so they went on to observe that good performance is also about making discoveries and having insights. And in a similar vein, what we found in analyzing military accidents and incidents is that good performance or expertise is much more than the absence of mistakes. It's also about being able to pull through mistakes. Now, I've deliberately chosen the words pull through here rather than say bounce back or rebound, because the system may not actually return to its earlier state or condition. And instead, it may simply migrate or evolve or adapt in line with unfolding events into a new or different safe state. Now, to me, the value of this perspective is that it actually recognizes the need for people to operate close to the boundaries of safe operation, particularly in time-pressured, high stakes, and dynamic situations, which confronts people in many domains, not just in the military, but in healthcare, emergency management, and so on. And so what happens in these demanding work settings is that so-called errors can occur when people experiment with pushing the envelope, such as the aerodynamic boundaries of safe flight, in their bids to save lives, defend against adversarial attacks, and so on. And so, as Jens Rasmussen recognized, what we need to do as analysts and designers is to develop designs that are tolerant to error. So in other words, designs that give people visibility of the boundaries so that they can operate closer to the edge if necessary without crossing the boundaries. And then in the event that the boundaries are crossed, so that they can detect and recover from those incidents. And ultimately, this perspective is really about designing for adaptation, because it deliberately supports people in adjusting their actions or activities in dealing with the demands of a wide variety of situations, including challenging and unpredictable events. And I think it's also important to note that this perspective may not only improve safety, but also effectiveness, because erring on the side of caution, many safety programs tend to impose very tight margins on performance, with the problem being that these margins tend to break down, pretty much all of the time, but particularly when out of the ordinary events occur. Okay, so how have we applied these ideas in an Air Force context? Well, in one of our key projects, we were asked about improving safety in strike fighter operations, particularly through training. And so we studied a number of aircraft accidents, which were fatal, unfortunately. And so we analyzed aircrew's problem-solving processes as best we could from the cockpit recordings. But we also studied many more incidents, which were important because we could actually interview the aircrew involved about how they, or their problem-solving processes and how they detected and recovered from those incidents. And so we use the critical decision method for the interviews, which is, of course, a key NDM tool, and that's reflected in the first step of the method that's illustrated on the right of the slide. And then in the second step, we represented the data from the interviews using decision ladders from the cognitive work analysis framework, which is also in the NDM tradition. And in the final step, we developed a number of training strategies based on the preceding analysis that didn't just focus on training aircrew not to make errors, but also in giving aircrew visibility of the boundaries of safe operation and experience in detecting and recovering from crossing the boundaries should that occur. And if you're interested in the details of this sort of method, I think that's best described in the paper that's noted at the bottom of this slide. So just as an example, imagine a situation in which the pilot of a fighter aircraft flying at low level, so pretty close to the ground, executes a pop-up tactical maneuver manually without first disengaging the autopilot. So the pilot then experiences difficulty in executing the maneuver because the autopilot is fighting him for control of the aircraft, but the pilot doesn't respond to those and other cues. And then because the autopilot disengages or releases while the pilot is still trying to fly against it, the aircraft is thrown into a hazardous attitude and then hits the ground. Now, in this case, the analysis on the right suggests that the pilot had difficulty in detecting the error, not because he didn't notice critical cues or information. I mean, he was clearly aware of the difficulty he was experiencing in flying the aircraft manually, but rather because he was unable to diagnose in time why that was the case. Now, if he had realized that the autopilot was still engaged, the chances are he could have safely disengaged the autopilot and recovered the aircraft to a safe flight. So from this case, a potential training strategy is that as well as training aircrew in the safe execution of this procedure, aircrew should also be given the opportunity to experience the effects of breakdowns in this procedure and to practice the problem-solving processes for detecting and recovering from that. And this kind of training strategy is consistent with the recognition prime decision-making model, which recognizes that particularly under time-critical conditions, experts can make quick and effective decisions by matching situations to prior experiences. So to assess this sort of training approach, we interviewed a number of aircrew and training instructors about, as shown in the second column of this table here, about whether they already conduct the training strategies we've identified. Then next, whether they think these training strategies are potentially useful. And lastly, whether they've been in similar unsafe situations to those that motivated the training strategies. And generally what we found was that they do not already conduct the training we identified, that they think the training could be useful for helping them deal with unsafe situations on actual operations, and that they have previously been in similar situations, suggesting that these unsafe states aren't all that rare. And so then a question is, well, how can these training strategies be implemented safely? Well, one possibility, and the most obvious possibility that comes to mind, is to use human-in-the-loop training simulators. But generally what we found is that these systems don't tend to simulate unsafe states. So for example, they might only allow pilots to practice executing a procedure correctly and don't simulate what might happen or how the aircraft might feel if there are breakdowns in this procedure. And so then some other training possibilities we can consider include mental rehearsal and case-based learning techniques, depending on the nature of the training strategy. But overall, there are broader implications here for the design of training systems as well, from this NDM perspective of safety and effectiveness in complex operations. So in wrapping up then, I just wanted to make the point that for me, NDM research is important in designing for adaptation. It helps us to understand why people may operate close to the boundaries of safe operation and how they may pull through in the event that the boundaries are crossed. And so our approach to accident and incident analysis deliberately recognizes that, firstly, that people's inherent ability to adapt may nudge them towards operating at the edge in order to guarantee system effectiveness in demanding situations. I mean, that's what makes these systems work. And secondly, that although people are fallible, their ability to adapt also makes them one of the most important lines of defense in averting an accident or incident. And that brings me back, I think, nicely to where I started, the paraphrase quote from Gary Klein and Corinne Wright, that good performance is much more than the absence of mistakes. And so that brings me to the end of my presentation. Thank you so much for listening.